morning, students. Myself, Vijay Shankar from BC Department, Civil Engineering College. Today, we are going to discuss about the convolution correlation. The introduction part of the convolution correlation, and we already seen the convolution derivation part and the theorems. I can see the one examples. Find the convolution of the signal x1 of t is equal to e power minus et mu of t, and x2 of t is equal to e power minus bt mu of t using the Fourier transform. Using the Fourier transform. So we know x1 of t is equal to given e power minus et mu of t means 1 by a plus 0. x2 of t is e power minus bt into mu of t, the b 1 by b plus 0. Using this relation, the Fourier transformation convolution, x1 of t with the convolution of x2 of t is a product of frequency, and inverse Fourier transformation you can apply, you get the convolution of the term. Okay, so we got the x1 of omega and x2 of omega, and apply the inverse Fourier transformation to get x1 of t with the convolution of x2 of t, because they're asking using the Fourier transformation how to find out. So first of all, you can get the time function 1 by a plus j omega and 1 by b plus j omega. So 1 by a plus j omega and 1 by b plus j omega, because the convolution time domain, the frequency is a product. So multiply the two functions, and 1 by a plus j omega and 1 by b plus j omega take as the two factors to find out a and the b values by taking a partial differentiation expansion method. A plus j omega plus j omega and b by b plus j omega. So this is for the x1 of t with the convolution of x2 of t is equal to. Okay. Now you can take the function 1 is equal to a into b plus j omega plus b into a plus j omega. A plus j omega. Compare the coefficients here, j omega coefficients and the constant values. If it is a constant, a into b plus b into a is equal to 1. And j omega coefficients, 0 is equal to a plus b, means a is equal to minus b. A is equal to minus b. Or b is equal to minus a. In that equation, you can substitute 1 is equal to a into b. Substitute the b as a value minus a into a. So a, you can take the common, b minus a is equal to 1. A is equal to 1 by b minus a. 1 by b minus a, and the b is equal to, so a is equal to the same, the minus only, the minus b minus a. So the x1 of t with the convolution of x2 of t, after applying the partial differentiation expansion method here, a got the 1 by b minus a, and the b got a minus 1 by b minus a. Take the b minus a is a common term, as a is 1, a plus j omega, a plus j omega minus 1 by b plus j omega. Okay, that is equal to, this is for the inverse Fourier transformation of the function, 1 by b minus a into, so what is the 1 by a plus j omega e power minus a t mu of t minus e power minus bt into mu of t. Okay, my dear students. Now using the Fourier transformation, the convolution of the time domain function x1 of t and x2 of t, we got 1 by b minus a into e power minus at minus e power minus bt into mu of t. What is my difference? See here. The 1 by b minus a e power minus at mu of t minus e power minus bt into mu of t. And second example is given here. It is also using the Fourier transformation only we have to find out. One is the 2 into e power minus t 2t mu of t and x2 of t is a mu of t. See, x1 of t is given as 2 into e power minus 2t mu of t. Its a Fourier transformation is x1 of omega is equal to 2 into 1 by 2 plus j omega. Okay, and second one is given the x2 of t is equal to mu of t. Then x1 of x2 of omega is equal to mu of t. The Fourier transformation is pi into delta of omega plus 1 by j omega. Is a Fourier transformation. Now we can multiply the two functions, 2 by 2 plus j omega multiplied with because x1 of omega into x2 of omega. The pi into delta of omega plus 1 by j omega. 1 by j omega. What it matters. Now you can multiply the 2 into pi delta omega by the 2 plus j omega and 2 by j omega into 2 plus j omega by using the partial fraction expansion method. Multiply the 2 pi delta omega by 2 plus j omega plus 2 into 2 plus j omega into j omega. Okay. Now find the factors here. A and B for these two functions. A we got the 1 and the B is equal to minus 1 by taking here, or otherwise directly you can find out the 2 is equal to A by the something means A into j omega plus B into 2 plus j omega. Okay, you can take only the coefficients constant, the B, the A, there is no any constant values, the B only. B is get cancelled, as a B is equal to 1. Compare the coefficients here. A j omega coefficients, 0 is equal to A plus B. A is equal to minus B, nothing but is a minus 1. A is equal to minus 1 and the B is equal to 1. So, if I take that value is A by something, A by 2 by j omega and 1 by j omega, we can write as plus A is minus 1 by 2 plus j omega, and here the term, another term is there, the plus 2 pi into delta omega by 2 plus j omega. Okay, 2 plus j omega. This is for the inverse Fourier transformation. Inverse Fourier transformation of this total function. Okay. Now, you can observe here, we got the same thing, 1 by j omega minus 1 by j omega plus 2 and this one. Since the delta omega is equal to 1 for omega is equal to 0, and delta omega is equal to 0 for omega is not equal to 0. Not equal to 0. Therefore, 2 pi into delta of omega. Delta of omega becomes, the value is j omega is equal to 0. When this omega is equal to 0, the delta of omega is equal to 1. 2 pi into delta of omega by j omega plus 2. When omega is equal to 0, the delta of omega is equal to 1. And omega is not equal to 0, delta of omega is equal to 0. Means we have only one value will get, remaining all the zeros on. Now I'm substituting omega is equal to 0 in the denominator, becomes of 2 pi delta of omega by 0 plus 2. The 2 to get cancelled, the pi into delta omega only becomes. So finally we got the 1 by j omega minus 1 by j omega plus 2 plus this total function becomes when omega is equal to 0, the pi into delta omega. Pi into delta omega. Got it, my dear friends? So pi delta omega plus 1 by j omega minus 1 by j omega plus 2. So pi delta omega 1 plus j omega, the inverse Fourier transformation is mu of t minus this total function is e power minus 2t mu of t. Okay, the x1 of t with the convolution of x2 of t is equal to mu of t minus e power minus 2t mu of t. Okay. The next topic is correlation. Until now, we discussed about the convolution only, the signal comparison or the correlation of the functions. The correlation, there is two types of the correlations we have, the cross correlation and the autocorrelation. What is a cross correlation and what is a autocorrelation? Before going to know the cross correlation and the correlation, you have to know what is the correlation first of all, the concept of correlation. The signals may be compared on the basis of similarity of waveforms. Quantitatively, a comparison may be based upon the amount of component of one waveform contained in the other waveform. The amount of component of one waveform contained in other waveform. If x1 of t and x2 of t are two waveforms, then the waveform x1 of t contains an amount of C12 of x2 of t of that particular waveform. X2 of t is in the interval t1 to t2, where, see, why are they saying here? We know the orthogonality function. What is the orthogonality? C is equal to orthogonality of signals. C is equal to integral t1 to t2 or minus infinite to infinite x1 of t, x2 of t dt whole divided by the integral t1 to t2 x square or x2, whatever in these two functions, you can take any one of the function, x2 square of t dt. Okay, this is orthogonality function. And c is equal to, when the c is equal to 0, the numerator becomes 0. So if any signals are given, the two signals, you can say that those are orthogonal. The integral t1 to t2 x1 of t x2 of t dt is equal to 0, you can prove, then the c is equal to 0. Okay. The magnitude of the interval in the numerator might be taken as an indication of similarities. Once again, you can see, my dear friends, the magnitude of the interval in the numerator might be taken as an indication of the similarity. If this integral vanishes, integral t1 to t2 x1 of t x2 of t dt is equal to 0, then the two signals have no similarity over the interval t1 to t2. There is no similarities over the interval t1 and t2. Such signals are said to be orthogonal over the specified interval. When this numerator term is the similarities indication, you can take the magnitude of the interval in the magnitude numerator might be taken as an indication of the similarity. If it is a 0, there is no any similarities between the two signals in the interval T1 to T2. That such signals we're calling it as an orthogonal signal. We know that. The integral T1 to T2 x1 of t, x2 of t, d2 forms the basis of comparison of two signals x1 and x2 for interval T1 to T2. In general, we're interested in comparison of two signals for the interval minus infinite to infinite. So the test integral becomes integral minus infinite to infinite x1 of t, x2 of t dt. Okay. How far it is a similarity means there is a one signal is a normal signal, another signal we can take as a shifted version of the signal. Okay. Both the signals, the total numerator becomes a 0. There is no any similarities between the two signals. When there is a similarity between the two signals, and we can call it as a correlation, means however there is a difficulty with the test integral, which can be illustrated with the example of the radar pulse, this one, and from the figures shows a transmitted pulse and a received pulse, which is delayed with respect to the transmission pulse with the t seconds. Transmitted pulse at the x1 of t, let us assume, and x2 of t is a received signal, and transmitted pulse with the ts. Obviously, the two waveforms are identical, except that one is delayed with respect to the other. Both the signals are the same, but there is a delay is there. At the test integral minus infinite to infinite x1 of t, x2 of t yields 0 because the product x1 and x2 is 0 everywhere. This indicates that the two waveforms have no measures of similarity, with obviously a wrong conclusion. Hence, in order to search for a signal comparison, whenever you can take the x1 of t and x2 of t, now change the integral value as the similarities between the two waveforms. We must shift one waveform with respect to the other by various amounts. See, therefore, the test integral is modified as integral minus infinite to infinite x1, and you can take the x2 is a delayed version, x2 of t minus tau. Tau samples is delayed, where the tau is a searching of our scanning parameter. The integral is a function of tau. This integral is known as a cross correlation function. Cross correlation function between x1 of t, x2 of t, and it is denoted with R12 of tau. So the R12 of tau is equal to integral minus infinite to infinite. Here I wrote the t minus tau, and here I wrote that t plus tau. Whatever it is, the delayed function or advanced function of any of the signal, x1 or x2, both the resultant value is the same in the convolution, not the convolution, sorry, correlation. So let us take R12 of tau is equal to, we are saying that is a minus infinite to infinite, x1 of t, x2 of t minus tau, beta, not the beta, dt on. Okay, and R12 of tau is also equal to integral minus infinite to infinite. Take any one of the signal is advanced function, x1 of t plus tau, x2 of t into dt. But don't take both the delayed versions. Got it, my students? Either you can keep x1 on the x2, or otherwise you can change the integral minus infinite to infinite x1 of t minus tau and x2 of dt also. and the integral minus infinite to infinite x1 of t, keep that it is a x2 is advanced function t plus tau dt. All the resultant value is the same. Okay, my dear students. Thus, the correlation of two functions or the signals or the waveforms is a measure of similarity between those signals. The correlation of two types, cross correlation and autocorrelation. The autocorrelation and cross correlation are defined separately for energy signals and the power signals. Energy signals are aperiodic and the power signals are the periodic signals. Got it, my dear students? And in these also, we can keep that any one of the signal is a complex signal also. Either it is a x2 or you can give the x1. Either you can take here the x2 is convolution, not the convolution conjugate, and x1 is a conjugate, even though the resultant value is the same. One signal is a normal signal, other signal is a delayed version of the signal. Then we can scan the parameter of the tau and we can measure of the similarity between those signals. Okay, the first you can see the cross correlation. What I wrote here, it is a cross correlation only. 1 and 2 is a different signals. The cross correlation between the two different waveforms or signals is a measure of similarity or match or relatedness or coherence, whatever it is the same. Similarity or the match or relatedness or the coherence between the one signal and the time delayed version of the other signal. One signal and time delayed, or one signal with the time advanced function, or one signal with the time delayed, whatever it is. This means the cross correlation between the two signals indicates how much one signal is related to the time delayed version of the other signal. Consider the two general complex signals x1 and x2 for the finite energy. The cross correlation of the two energy signals is denoted as R12 of tau is given as x1 of t, x2 star of t minus tau dt. It is also equal to integral minus infinite to infinite x1 of t plus tau, x2 star of t dt. Is both the complex functions. And now, if it is a real term, if the two signals x1 of t, x2 of t are the real, then R12 of tau is equal to, without the complex function here, x1 of t and x2 of t minus tau dt. And the second function without the complex x1 of t plus tau, x2 of t dt. If x1 and x2 have same similarities, then the cross correlation R12 of tau will have some finite value over the range of tau. Okay. Also, if the integral minus infinite to infinite x1 and x conjugate dt is equal to 0, R12 of 0 is equal to 0, then these two signals are called as orthogonal signals. Means there is no any similarities. Orthogonal means there is no any similarities between the two signals. Got it, my dear students? There is no any similarities between the two signals. Okay. Next, another form of cross correlation between x1 and x2 and x1 is defined as integral minus infinite to infinite x2 of t and x1 of t minus c. This is a function I wrote here. Any one of the function is a complex. You can take any complex function x2 here. Take the complex here. x2 of t and x1 of t minus tau dt. Okay. And another one is also see in the above equations, the cross correlation function R1 of tau is a function of variable tau. The variable tau is called delayed parameter or scanning parameter or stitching parameter. Always we are default saying that is a delay parameter. Okay. It is a time delay or time shift of one of the two signals. The delay parameter tau determines the correlation between of the two signals. The two signals with a cross correlation at tau is equal to 0, can have a significant cross correlation by adjusting the parameter. The two signals for which the cross correlation is 0 for all the values of tau are called as uncorrelated or incoherent signals. Incoherent signals, or nothing but is orthogonal signals. Is a 0 whenever can get the x1 and x2 of t minus tau is equal to 0. There is no any similarities, we can call it as a uncorrelated, or otherwise we can also call it as orthogonal. Let us see the properties of cross correlation function for energy signals. Properties of cross correlation functions for energy signals. The first one is a cross correlation exhibits a conjugate symmetry. Conjugate symmetry. R12 of tau is equal to R21 star of minus tau. Okay, when these two are equal, R12 and 2 commutative property means we can interchange the positions R12 of tau and R21 of tau is not equal here in the correlation. When these two are equal, whenever you can change the sign function, the 2-1 of minus tau, or it is a complex also. R12 of tau is equal to R21 conjugate of minus tau. That is, unlike convolution, cross correlation is not a general commutative. General commutative. Let us see the R12 of tau is equal to integral minus infinite to infinite x1 of t, x2 of t minus tau dt. Okay. Now I am interchanging the functions. R21 of tau is equal to integral minus infinite to infinite, and you can take the star also, x2 of t, x1 of t minus tau dt whole star. Nothing but is a conjugate of function. It also replace the minus tau. So R, here the conjugate, R21 conjugate of tau minus tau is equal to integral minus infinite to infinite. In suppose we can take here the internally, any one is a complex function. Let us take the complex function of these two. Now the multiplying the conjugate, it becomes x2 of t and x1 conjugate of t minus of minus, it becomes a plus dt. Now both are the equal. Advanced function and here the delayed function we get. Then only can both are equal. Otherwise, when we can change 1 to 2 to 2-1, it is not equal. When the tau is equal to tau. When the tau is equal to minus tau, the interchanges values only the equal. Got it, my students? And var 1, 2 of 0 is equal to 0. If both the complex functions is a 0, then the two signals are said to be orthogonal over the entire interval. We know this, the first unit itself, we know the x1 of t with the x2 conjugate of t dt is equal to 0. Both the signals are orthogonal. And cross correlation of two energy signals correspond to the multiplication of the Fourier transformation. Means R12 of tau, the Fourier transformation is product only, but that product, one is a real function, another one is a conjugate function. Got it, my students? These are the three properties of cross correlation for energy signals, aperiodic signals, or cross correlation for the power signals, something but the periodic signals. the periodic signals, the t is 1 by t. Whenever you can represent the t means it's a periodic signals only with the period of t. The cross correlation function R12 of tau for two periodic signals, one is x1 and x2 of t may be defined with the help of average of the correlation. If the two periodic signals x1 and x2 have same time period t, the formula is a 1 by 2 the integral minus t by 2 the t by 2 x1 of t and x2 star of t minus t dt. Then the two signals x1 and x2 are called orthogonal signal. That is a cross correlation for orthogonal is a 0. Okay. Another form, the cross correlation x1 and x2 is defined as R21 of tau is equal to R21 of tau is equal to integral minus infinite to infinite. X1 I'm changing as x2 and x2 is changed as x1, x1 star of t minus tau dt. Now you can see the properties of cross correlation function for the power signals. See, when these two signals are orthogonal, the cross correlation of energy signals have three properties, and cross correlation for the periodic signals x1 and x2 are both are orthogonal. That is a cross correlation of orthogonal signal. Another form is R21 of tau is equal to, this is the equation for the correlation function, that to cross correlation function. The above equation, the cross correlation function R12 of tau is a function of the variable tau only. It's uncorrelated and correlated. Already we discussed that one. Okay, the cross correlation of two periodic functions defined another form. R21 is a 1 by 2 the integral minus t by 2 the t by 2. x1 and x2 here and changes as x2 and x1. Okay. Now see the periodic functions. The first one is a Fourier transformation of cross correlation of two signals is equal to the multiplication of Fourier transformation as usual. R12 of tau is x1 of omega and x2 star of omega. And R12 of 0 is equal to 0. It becomes of orthogonal. Then the signals are said to be the orthogonal over the entire time interval. And in this power signal also, R12 of tau is equal to R21 conjugate of minus tau, not the plus tau. Unlike the convolution, the cross correlation is not commutative. Cross correlation is not commutative. Let us see that is a proof. R12 of tau is equal to R21 star of minus tau. The cross correlation exhibits conjugate symmetry. Let you take the R12 of tau. The formula, one signal is a delayed and another signal is a normal signal. That I am taking the x1 of t, x2 of t minus tau dt, and one is a conjugate of. Okay. Let t is equal to here, taking that let t is equal to tau and tau is equal to n in the above equation. So for our convenience, I am changing the values as t as n. Now R12 of tau is equal to integral minus infinite to infinite x1 of the t minus tau is equal to, let us see here, t minus tau is equal to n, when the t is equal to n plus tau, and x2 star of t minus tau, we assume the n, and dt is t is equal to dn. Apply the derivative here. The dt tau is a constant, dn. and this is a let t is equal to t minus tau, and R12 of tau is equal to integral minus infinite to infinite. We have one is a complex, another one is a normal function. Now we got the advanced function here, x1 of n plus tau and x2 star of n with the dn. Another function we can assume here, x2 of t and x1 star of t minus tau dt. When I am assuming the x1t and x2 star, now change is x1 as x2 here and changing that x2 as x1. Okay. Now replace t is equal to n. T is equal to n. So R12 of, not the 1 to 2 1 minus 2 1 of tau. 2 1 of tau is equal to integral minus infinite to infinite x2 of n and x1 star of n minus tau dn. Okay. Now replace the 2 1 star, the conjugate for the both sides, R 2 1 of tau is equal to the conjugate also, and change the minus tau here, integral minus infinite to infinite x2 of n x star of our conjugate of n minus of minus tau into dn whole conjugate. Because in this function, whatever we have here, in this function, I'm replacing tau as minus tau and taking the conjugate whole. So integral minus infinite to infinite x2 of n with this conjugate becomes x2 conjugate of n. Conjugate of conjugate is only the real term. N minus of minus is a plus, n plus tau dn. So R21 of minus tau conjugate, we got this expression. Already we know R12 of tau is equal to the same function of x1 of n plus tau and x2 conjugate of n and the dn. Means in the left hand side, the R12 of tau here, and in this equation, the right left hand side, let us take this as 2 equation, and this one is of 1 equation. From 1 and 2, left hand side R12 of tau is equal to, here in the left hand side R21 of minus tau whole conjugate. Okay. Unlike the convolution, the correlation is not a commutative. Understood, my dear students? So we got the R12 of tau is equal to R21 star of minus tau. Got it, my dear students?